Good morning, everybody. Today we're going to talk about waves and the introduction of waves. We will talk about some properties of waves, the two different types of waves. Okay, let's just start. All right, waves. Now, waves is another mean of actually transferring energy from one point to another, yeah? Without being transferred of matter between the 2 points. This is important, and you will see later when we talk about the different types of waves, okay? So, every time when I do a slideshow, please make some notes. Just pause the video. I show you the screen clearly, and then you can make notes. Okay? All right. Two different types of waves. First, we're going to talk about the transverse waves. What are transverse waves? Yeah. Transverse waves are waves wherein the vibration of a particle is at 90 degrees to the direction the wave travels. Yeah? In the IGCSE, you actually have to explain the movement of the particles and the progression of the waves. Okay? So, what does it mean? The vibration is up and down, and the wave direction is in this direction. Okay? Transverse waves. Okay? A clear example of transverse waves is water waves, mechanical waves, other wave or type of wave of transverse waves, is light. Light is also a wave. But we will discuss light and sound in another slide. So important to know, again, vibration up and down and the wave direction in one way. Now, if I would look at, if I would put here a cork and I would look at the transfer waves, now, and here is my cork. Cork is not going to move in the direction of the wave direction, but the cork is like moving up and down. So that's why I say the particles are moving up and down, but the progression of the wave is in that way. Okay? Don't forget that. Later I will show you a video clearly what are transverse waves. Okay? Now, what is the other type of wave? You might have heard about it. Longitudinal waves. Yeah? Longitudinal waves are waves where the vibration of the particles are along the direction in which the waves travels. Yeah? So, vibration is now parallel to the wave direction. This is a longitudinal wave. And a clear example is sound waves. Yeah? Sound waves are a clear wave of longitudinal waves wherein the particles are moving like that. So when I'm speaking to you, the wave is traveling through the air, and let's say here is an air particle. That air particle is moving around an equilibrium, is moving like that. But the progression of the wave is towards you. Okay? Now, normally we will give a demonstration and to show you with a slinky what is the difference between a longitudinal wave and a slinky. Okay? So, I give you time to make some notes, so pause again the video and make some notes. Alright. Okay. Let's look at the video of a transverse wave. And let's look at this wave. Transverse waves. Okay, now what we see here, we see that the wave progression is this direction. And look at this particle here. That particle, so again, look at this wave and see how the wave progresses in this direction. Okay, but the particle is moving up and down 90 degrees towards the wave propagation. Okay, so normally I would demonstrate that to you, or you could do yourself. Yeah, you stretch the slinky and you're going to move it like sideways on the ground, and you will see a clear transverse wave. And look at the particles. Yeah. Yeah, you see here this particle here. What is happening with that particle? It's moving this way while the wave is moving this way. So the particle, the vibration is always to 90 degrees. Okay? Now we're going to look at a longitudinal wave. And we are going to look again at the vibration of the particle. Okay? So with this wrinkle, yes, like you push it forward, yeah? And that is the direction of the wave. Okay? And look how this part is moving. It's moving around the equilibrium. Okay? Now, let's have a closer look. Yeah, and now look at this. Look at this. Look at this. What do we see? The wave is propagating in this direction, as we have here the particle that is moving parallel along the wave travel. So, vibration parallel to the direction of the wave. Don't forget these two, longitudinal and transverse. Transverse waves we find in sea waves, in light. Longitudinal waves we find particularly in sound waves. Okay? All right, even a closer look and see that it comes back to its beginning point, yeah? So more or less the particle always stays around the same position, okay? All right, let's go back to our slideshow, okay? Now we're going to describe waves. And what do you need to know about waves? Okay? Well, you need to know what is the amplitude. The amplitude is the maximum movement of the particles that they make from their rest position. And let's look at the wave. Yeah? And you might have seen this already. So we can actually see where the amplitude. Important to note that this is the rest position, okay? And then you could describe the amplitude as on the top, or from the rest to the top, or from the rest to the bottom. Okay? Now, the amplitude is the height of a crest, or the depth and the throw. So this we call, make a note of that. Crest, and this is a throw. A throw. Okay? So amplitude is always from its rest position to the top, or from its rest position to the bottom. Okay? Make a note of that. Alright, so now we know what we mean by the amplitude. Okay? What is the wavelength? The wavelength is the distance between one wave peak to the next wave peak along the path of a wave. Now remember, we measure always in normal SI units, so in meters. Okay? So, how would we describe a wavelength? Yeah, in this way, you could describe it from crest to the next crest, or from throw to the next throw. Okay? And this is how we describe the wavelength. It's a distance in meters. Right? Make a note of that, and then we move on. Alright. Now, obviously, a wave is vibration. Sound is vibration. Yeah? And light is vibration. That means they all have like a frequency. Okay? Frequency is the number of wave peaks that pass in 1 second. Or we may say that is the time taken for one wave. Okay? Or we may say it is the amount of vibration in 1 second. The unit, you might have heard of it, is measured in hertz. So 1 hertz would actually represent 1 peak per second. If we have 2 peaks per second, we have a frequency of 2. Okay? So when we have 1,000 peaks per second, we're talking about kilohertz. Okay? 1 kilohertz is 1,000 hertz. And 1 megahertz is 1 times 10 to the power of 6 hertz, or 1 million hertz. And again, make a note of that. Okay? 1 gigahertz is 1 billion hertz. Okay? Normally hearing, sound that you can hear is about between 20 hertz and 17, 18 hertz. 1,000 hertz, sorry, or 17, 18 kilohertz, right? So this is how we describe the frequency of a wave. Make a note, and then we continue. All right. What do we mean by the time period? Yeah, the time period is the time taken for the source to produce one wave. Okay? And for that time, we can actually find the time period, because the time period is 1 over the frequency. Okay? Now let's look at the wave. Here I have my wave. And this one is progressing in that direction, and let's say for one wave of 1 complete vibration until it comes back to the same point. Okay, so, okay, one wave. Okay, let's say one peak that passes, and it does in, let's say, 0.1 second. Then the frequency is 10 hertz, yeah, because there are 10 peaks passing in 1 second. And then we can find the time period is 1 over 10 is 0.1 second. Okay? Just make a note of that. Okay? All right. So T is 1 over F, and the frequency obviously is again 1 over the time period. Okay? I will give you later some questions and then you can make some calculations, okay? So first, make a note of this. Now let's look here. Let's say this wave is passing in 1 second. Now we have to calculate how many waves are passing, how many peaks are passing. 1, 2, 3. So we have 3 peaks in 1 second. Then the frequency is 3 hertz, and the time period is 1 over 3. And the time period is seconds. Okay? Okay. I'm going to show you some questions. So, copy first, and then I will show you the answers. So, first question is here. Calculate the frequency of a wave of a time period of 8 seconds. So, pause the video and make your calculation. Now, we know that the frequency is 1 over t is 1 over 8, and in this case the frequency is 0.125 hertz. Next question. Pause the video. Calculate the time period of a wave of frequency 50 hertz. Pause it. The answer, T is 1 over F is 1 over 50 is 0.02 seconds. Okay? Alright. Now let's talk about the wave equation, and you have to memorize the wave equations. Now, we know already something about the speed, the frequency, something about the wavelength. So there's also a relation with the speed. Now the speed is equal to the frequency times the wavelength. Okay? So in formula, V equals F times lambda. And now see already which symbols we are using. We are using F for the frequency and lambda for the wavelength. and the wavelength is in meters, frequency is in hertz, and the speed is in meters per second. Okay? So, speed in meters per second, wavelength in meters, and the frequency in hertz. Alright? Or we may rewrite the equation and we can say F is V divided by F, or lambda is V divided by F, and you might make use of the triangle, yeah? If you want to find lambda, lambda is V over F. If you want to find the frequency, frequency is V over lambda. Or if you want to find the speed is F times lambda. Okay? Pause the video, make a note, and then we move on. Alright, first question. Pause the video and try to answer the question. Calculate the speed of a water wave of a wavelength 3 meters and a frequency of 6 hertz. Then V equals F times lambda is 6 times 3 is 18 meters per second. The next question. Pause the video and try to find the frequency of a wave with a wavelength of 2 meters and a speed of 16 meters per second. V equals F times lambda becomes F equals V divided by lambda. Just to make you know, we write this like lambda, lambda, okay, how you pronounce it. F equals V over lambda, 16 divided by 2 is 8 hertz, okay? One more, there will be more. Calculate the wavelength of sound wave in water, frequency is given. 300 hertz, speed 1500 meters per second. Pause the video and answer the question. V equals F times lambda becomes lambda is V over F. 1500 meters divided by 300 hertz is 5 meters. Okay? Oh, sorry, I go a little bit too fast. Yeah? 5 meters. Alright, our next question. The time period. Calculate the speed of a wave that has a wavelength of 30 meters and a time period of 0.04. So, in this question, you have to find the frequency first, and then you can calculate the speed. Pause the video and answer the question. F is 1 over t, 1 over 0.04 seconds. F is 25 hertz. V is F times lambda, is 25 times 30 is 750 meters per second. Okay? Alright, try to complete this table, yeah, copy, and then find the answers for the speed. In the first one, frequency, the second one, frequency in the third one, and the wavelength in the last one. Make note that here, in the last one, we have kilometers per second, so you have to write it down, and in meters per second. Here we have megahertz, and megahertz is for 1 mega is 1 million. Pause it. Okay. Answers. First one, 60 meters per second. Second one, 165 hertz. There, Third one, 200,000 hertz or 200 kilohertz. And the last one is 3 meters. Okay? Now, when we make calculations of waves, and it doesn't matter if it is a mechanical wave, like a water wave, or when it's a radio wave, or light waves, we always can use this formula, the wave equation. Okay? So no matter what, all waves behave exactly the same. Yeah? Alright. The last part that I want to discuss with you on this slide is the diffraction of a wave. Okay? Now, it's interesting to know what diffraction actually is. And hopefully I can demonstrate in this class what we mean by diffraction. So I'm going outside the door and I will speak in the hallway and see if you still can hear me. Now the microphone is a little bit awkward place, so let's see. So I'm going out. And now I'm talking to you in the hall, and I'm talking to the toilet, and I think you'll still be able to hear me, yeah? While keeping the door open. It might be not so as loud, but you can still hear me. So, I was standing outside in the corridor, and was more or less walking towards the toilet and speaking from the toilet into the hallway or towards the toilet, doesn't matter. Now what happens is I kept the door open, so there's a one way and another is that a wave can bend around an opening or edges, and this is what we call diffraction. Yeah? What is diffraction? Diffraction occurs when a wave spreads out after passing a gap or a round obstacle. And let's look at this example. Okay? So waves are coming in, and what we see here, we see that the waves are spreading out. Straight waves are coming here and they're like spreading out, they're like bending around, okay? Another example here is light diffraction of a razor blade, yeah? And we get a special pattern, okay? Now, in order to know how, when diffraction occurs more and about which situation, now let's look at our next example. If the gap is very open and relatively big or much bigger than the wavelength, then actually you get a little bit of diffraction. Okay? So the first example, the opening is much bigger than here, the wavelength, the two peaks, remember two peaks wavelength, so they will bend just a little bit. Now, what is going to happen if we close that gap? What will happen with the diffraction? Now, the opening is about the size or smaller than the wavelength, yeah? So again, in a water wave, we can denote the wave like this, yeah, from one top to the other. That's the wavelength, lambda, remember. Now when the opening is much smaller, simply the waves are going to bend much more. I'm going to watch a video of diffraction, and normally we do a demonstration with a water tank. Or we call it a ripple tank. Well, we don't want to see this, but we skip this. Okay. And we apertures actually the amount of openings. Okay. Normally we could make a demonstration for the water tank. Yeah. We have a tip of the needle, and it is actually creating a circular wave front. Now we made an opening, okay, opening with two glass plates, and the wave is actually entering the opening. And let's see what is happening. And now we get the effect, yeah? We see that the waves are bending quite a lot around the opening, okay? And this is what we call diffraction, yeah? A clear example of diffraction, yeah? And the amount of diffraction depends on the sides, the opening size of A and B in this case, okay? Another example of light waves that diffract. This is light, and obviously as the wavelength of light is very small, the opening needs to be very small. Okay? Now, as I said, opening or edges. Yeah? So, if we have only one edge, yeah, also waves will bend around the edges. This is also called diffraction. So it is the bending of a wave around an obstacle. And what do we see? We see that the waves are bending around B and D. Okay? All right. To conclude our slideshow, let's answer some questions. Fill the questions in. So pause the video and try to fill in the question. Pause. All right, a wave transfers energy without the movement of a matter from one place to another. In a transverse wave, the particles vibrations are perpendicular to the direction of the wave travel. Frequencies equal to the number of waves produced in the wave in 1 second. The time period is equal to the reciprocal of the frequency. The speed of the wave in meters per second is equal to its wavelength in meters multiplied by its frequency in hertz. Okay? If you want to see more online simulations, I will send you later the PowerPoint so you can walk through it again, but I advise you first watch the video. Well guys, that's it for today. Next lesson we will continue talking about waves and light and sound. Okay, have a good day.